Hey there, and welcome to AI Lab 99. This is the very first app in the series of several AI-powered applications we'll be building together. We'll start with simple foundational machine learning models and gradually work our way up to more advanced systems, including generative AI. For every project we build, we'll also create a web app, so it's accessible and interactive for the end users. Let's dive into the journey of building smart, deployable AI one app at a time. The first app will be the housing price predictor, which estimates the home prices based on the square footage. We'll be working with a dataset that contains home prices mapped to their square footage. Our goal here is to build a model that can accurately estimate the house prices based on area. To solve this, we'll use the most straightforward machine learning technique, which is linear regression, and deploy the model as a simple interactive web app as shown here. All right, let's start by installing the necessary packages. Pip install Jupyter, Pandas, Matplotlib, scikit-learn, and Streamlit. Once that is done, we'll launch the Jupyter notebook. Now go ahead and create a new notebook. We'll begin by importing Pandas. Import Pandas as PD. Now let's load our dataset into a data frame. And to quickly take a look at the first few rows, we'll use df.head. We can see that there are two columns, area and square footage, and price of the home in dollars. Now let's run df.describe to take a look at the stats. We can see that the count is 500, which means there are 500 data points. The minimum area in the dataset is 390 square foot, and the maximum area is around 4,200 square foot, whereas the average is 2,100 square foot. The price, on the other hand, minimum price is $275,000, maximum is around $3.2 million, and the average is around $1.5 million. These stats will help get a quick overview of the data we have. Now let's go ahead and plot the data. Importing Matplotlib. I want to create a scatter plot with square footage on x-axis and the price on y-axis. Adding the title of the plot and labeling the x and y axis by using x label and y label, we see that there is a clear upward trend in the data. As the area of the house increases, the price also increases. This tells us there's a strong correlation between the area and price, right? We can also see that the data is not perfectly linear too. There is some noise in the higher square footage range, which makes sense because not all the houses with the same square footage will be priced the same. Now, before going ahead to build the model, I want to separate my feature set and the target variable. Now let's take X as the feature and add the area column. Y will be the target variable, which is the price. Now let's split the dataset into train and test sets, importing the train test split from scikit-learn. I want to split both X and Y, so adding them as arguments and specifying the test dataset size to 0.2 and a random state so that I get the same split when I run this code again. This function will give four variables: xtrain, xtest, ytrain, and ytest. Let's print the shape of these variables. We can see that there are 400 data points in the train set and 100 data points in the test set. When we specified the test size to 0.2, we are taking 20% of 500 data points in the test set and 80% in the train set. Now let's use these datasets to build our linear regression model, importing linear regression from scikit-learn, creating a model and executing model.fit on xtrain and ytrain. And that's all. We have the model ready. Let's make a prediction on this model. We'll run model.predict and the input would be the area of the house. Let's give 1,000. It says around $793,000. So the model thinks that a house with an area of 1,000 square footage costs around $793,000. Now this is just one prediction. Let's visualize the model's predictions along the scatter plot we have. using the same code that we executed earlier. On top of this scatter plot, let's plot a line that plots area on x-axis and the model's predictions on y-axis. The red line here is called the line of best fit. We can see that the line does a solid job capturing the general trend. As the area increases, the price increases. That's exactly what we expected, but we can also see that between 3,000 and 4,000 square foot, the points start to scatter above and below the line. That's where the model is not quite as confident, and it shows there is more variability in pricing for larger homes. Let's just verify the visualization by running model.predict on 4,000. The output is around 2.8 million, which matches the value that is shown in the plot. Now, how do we interpret this model? We see that the model has come up with a straight line. Mathematically speaking, we can define a straight line in terms of an equation. From your high school, you must be familiar with the equation of the straight line that is y equals mx plus c. In terms of this use case, y represents the price of the house, x represents the area, which serves as input to the model. M is the slope, which determines how much the model is tilting towards or away from the x-axis. And there is C, the y-intercept, which tells us where the line is cutting the y-axis. And the same equation in terminal machine learning is written as y equals mx plus b. Again, y is the price, x is the area, w is the slope, but it is also called as a weight or a coefficient. The b value, which is the y-intercept, is also called as bias. Now, when we executed model.train, the model has come up with these values of w and b, so that for any given input x, which is the area, the price of the house is calculated using this formula. Now that we know the underlying equation of the model, let's check out the values of w and b obtained by the model. The weight or the coefficient of the model can be obtained by model.coefficient, and the bias is obtained by model.intercept. We see that the coefficient is around 670 and the bias is around 122.6K. Now that we know the weight and bias of the model, we can write our own predict function. Let's define the function predict housing price, which takes area as parameter. The formula is coefficient times area plus bias, which is 670 times area plus 122.6K. Let's test this function, giving it 1,000 as input. It says $793,000, which is the same as the one that is given by model.predict function. At this point, we trained the model, found out the coefficient and bias, and have also written our own predict function. Now, what are the findings that we can observe from this line equation? Looking at this equation, we can say that if the area is 0, the price of the house is $122.6 thousand. However, it is important to understand that a house with 0 square footage does not really exist in reality. This intercept should be interpreted as the estimated base value of the house that usually captures the fixed costs. That is the significance of the bias term. Apart from that, when we look at the coefficient term, we can say that on top of the base value of 122.6K, for every 1 square footage increase in area, the price of the house increases by $670, right? Which means every 100 square footage increase would contribute to $67,000 to the price of the house. This information can be used either by homeowners to plan their purchase or by the realtors who want to assess the housing market conditions. In the final step, let's quantify the performance of the model. Until now, we have only seen the visualization of the model's prediction, but now we'll calculate the root mean squared error, which gives a mathematical insight on how well the model is performing. Importing mean squared error from scikit-learn. This function takes two inputs, the actual housing price values and the predicted housing price values, giving in the train values. This gives us mean squared error, but when we add a square root, we get the root mean squared error. So this gives the train RMSE. Let's calculate the same for test data points. printing both the values, we can see that the RMSE on train predictions is around 270,000 and the RMSE on test predictions is around 237,000. This means that when the model predicts a housing price to be around 500,000, the actual value of the house might be plus or minus 270,000, which means like around 200 to 770,000. This might look like a huge margin of error, but this has already been observed in the visualization because there is a larger spread in the housing price as the area increases. So I'd probably rely on this model for predicting price on smaller homes, as that might give more accurate predictions. The second point is that the RMSE on test data, which is around 237,000, is something that the model has achieved on the unseen data, which is close to its RMSE on trained data. This means that the model is reliable on new data points. With that, we have concluded the model building part. Now let's create an interactive web app. I just created a new Python file. We'll use the Streamlit package to build the app, importing Streamlit, adding a title, which will be displayed on the home screen, adding a prompt for the user to enter the area of the house to predict the price, adding a number input field that takes in the area. Minimum value is 0 and the step is 100. Adding a button called submit. Now when the button is clicked, the price should be calculated and should be displayed on the screen, right? Let's bring in the custom prediction function that we have written earlier. Using this function to make prediction from area, adding a success message that displays the price of the house. That's pretty much it. Let's run this file, running the command streamlit run app.py. And here is the web page with the title, the prompt, and the input field. Let's give in the input as 1000 and submit. We see the prediction of $793,000. Increasing this to 1500, we see the prediction, and so on. With this, we have successfully built and deployed our first machine learning project from start to finish. All the code and the dataset is available in the GitHub repository linked below. Until next time, happy coding.